I have the course webpage up so that I can let you know that your next thing to do is available. So everybody finished homework 0. That means everybody like submitted it correctly. I think that's never happened in a semester before, that like no one screwed it up and forgot to submit. So good job, everybody. This is excellent. Formative assessment number 1 is the next thing that I have for you to do. That is inside Icon under quizzes, but don't let the name fool you. It is not a quiz. It is an opportunity for you to earn 2 points for trying to answer my questions. And if you get the answers wrong, I don't care. The point is to try. The questions that are on there are things we're going to be talking about this week. So I'm hopefully by the end of Thursday, you'll be able to answer all of them. And then we will go over them on Tuesday's class. That's why they're due Monday nights, so that I can read through all the answers and get a sense of any common questions or points of confusion or clarification, and then we'll talk about it on Tuesday. So 3 of the questions are about this week's review content. The fourth, needs a little bit of explanation. So for those of you who have not been in a class with me before, one of the things that I like to do at the beginning of the semester is to ask everybody to provide a theme song for themselves. So like if you were playing in the Super Bowl or the World Cup or some other like big athletic arena and you enter the game, like what is the song that's playing on the overhead? Like what do you envision for yourself? And it can be any language, any genre. I especially like people who suggest new music that I can exercise to because my tastes are quite old. I would say that there's no incorrect answers except one time somebody put down Christmas music and I said, I'm sorry, that is incorrect. You cannot have like Silent Night as your theme song. That doesn't work. But other than that, what I would like for you to do is put in a link to YouTube if I can find the song, and I will build a compilation for the class and share it with you as an unlisted playlist so that we can all share each other's songs. If you don't want to have it on YouTube, let me know and I won't put it on there. But otherwise, I hope that you'll play along so we can kind of get to know each other that way. So that's the 4th question that merits that explanation. Today, this week, and for next week, we've got review material, at least what I'm considering to be review material. I realize that in statistics especially, there's a lot of different ways to explain the same thing, a lot of different notation, vocabulary, program syntax, and so I want to try and make sure that I get as many of us onto the same page as the way that I'm going to talk about stuff, if you haven't had this type of material from me before we get into things that are ostensibly new. So everything that I have to say should be something that you've at least heard of before, if not done. And if not, well then it's not a review, it's new material and we're covering it anyway. This will be what your first actual homework is about, a general linear models exercise. So any questions before we dive into some new, maybe not new stuff? Good to go? All right, then away we go. Well, I will be interweaving lecture and example, so this will take as long as it takes. That's sort of my philosophy. And I'm watching the chat window, Zoomers, if you want to post questions there, or you can talk, it's up to you. And if any of you have questions at any point, please stop me. This is supposed to be more of a dialogue than like a monologue, ideally. All right, away we go. So naming conventions. Starting with general linear model as an umbrella term, all of these types of specific models are special cases. So the big common thread is that this is a model that's designed to predict independent observations where the outcome is something that's continuous and the residuals of that outcome when you're done predicting it are supposed to be plausibly normally distributed. So special cases then, if I'm predicting one outcome and I'm doing it with a categorical predictor or a grouping variable, I would call that an ANOVA. A one-way ANOVA if it's one variable. If it's 2 variables at the same time, I would call that two-way. If I have quantitative predictors, so numbers rather than kinds, I would call that a regression. If it's one predictor, people call that simple regression. If it's multiple predictors, they call that multiple. Sometimes the word linear gets thrown in there as well. Linear is in contrast to what the rest of this class is about, which would be predicting nonlinear outcomes using nonlinear models. If you have both types, some people will call that ANCOVA, analysis of covariance or regression, depending on the textbook. If you have multiple outcomes, that's typically called MANOVA, if you're interested in group differences for multiple outcomes at the same time. If you have multiple outcomes and multiple quantitative predictors, that might be called regression or MANCOVA. All of these things are special cases of one idea, though. The key thread is that the residuals are supposed to be normal. One common misconception, oh, share my screen. I did that again, didn't I? Thank you, Zoomers. I always have everything going and then I forget like the most basic Zoom etiquette. Sorry about that. Okay, I'm on slide 2. One common misconception is with respect to predictors. So when people talk about variables having to be normal, it's not the variable, it's the residuals. It's the leftover part that has distributional assumptions. And predictors do not have assumptions. So if you have a continuous variable and you're interested in using that as a predictor of something else, that continuous variable does not have to be normally distributed. That is not a thing. Otherwise, we couldn't have something like ANOVA because it's categories and not a continuous variable. So the assumptions that we talk about are never about the predictors, they're always about the outcome. And the reason that we say we have the assumptions is because those are the rules by which we're computing height. That's what it boils down to. The distribution that we picked as our way to compute the height to settle on what parameters make our data the tallest collectively, that governs the assumptions. Because if the data don't follow that distribution, then using that formula for height isn't going to necessarily give you the best answer. All of these labels refer to the use of an estimation technique called ordinary least squares. So that's what you know of if you're computing sums of squares this and sums of squares that, all of that stuff. So here's an example of a general linear model starting from the very, very beginning. So what is known as an empty model. This is not something that gets taught in regression by everybody, but it's the place that I start because it's pedagogically useful, not necessarily something you would do in your life. The term empty means no predictors at all. So an empty model is just these three things here. Y sub I, Y for each individual. Beta 0, that thing is my fixed intercept. And E sub I is either the error or the residual for each person. So here's an example data set. I have income in thousands of dollars on the y-axis here. I have education as the x-axis, and I have 0 in the middle of the plot here because I have centered education at 12 years. Centered means subtract a constant so that 0 is somewhere in the scale of your predictor. So I don't have education in the model yet, though. All I have is this beta 0. So if I don't know anything else about a person, what's my best guess for their outcome? I heard it. The mean, right? That's what beta 0 is going to be. So in this data set, the prediction given by this empty model, this tiny little equation right here, is this purple line. The mean of this outcome is 17.3 in thousands of dollars. Now what if I wanted to predict income for this person right here? Look at all the money they make because they went to school for 20 years. Returning to our previous conversation. $58,000. Yes, this is an older data set. Although, if you want an academic job, that's probably not far off. If I'm predicting income for this person, then the mean is not a very good guess. They're much further above the mean. So their residual, it would be 41.5 to get them up to the 58.8 that they have. So at this point, residual variance, the variance of these e's across people, which is computed right here, y for each person, minus what y is predicted to be. So this symbol right here is called y hat. Right now, y hat is predicted to be the same number for everybody. Beta 0, 17.3 for everyone. So I take how far off are you from that prediction, square it, sum it across people, divide by n minus 1 because I had to figure out what beta 0 was to do this at all. That's why it's minus 1. And then the variance across people of these e's is 190. That's all the variance in this variable. Like that's the starting point. This is literally just the formula for variance that you saw in like undergraduate stat in a model. This is the starting point. From here, everything we do is designed to make this variance smaller, to explain it, to account for it, however you want to say it. So what if we throw in education? Income should be related to education. So if we fit a line for the effect of education, then we have two terms here that are fixed effects. Beta 0 is my intercept still. Beta 1 is my slope. Now beta 0 is not going to be the mean. Now it's going to be the expected income when my education predictor is 0, which, given the way that I've centered it, is for someone with a high school degree. So now beta 0 is the expected income for someone with 12 years of education. In this data, that worked out to be 14. Beta 1 is a slope. Change in y for a 1-unit change in x. In this context, this is the difference in education for each additional year, or excuse me, the difference in income for each additional year of education. It works out to be 1.8. Well, for this person, they have 8 more years of education than the centering point. So they don't have 20, they have 8, because 0 is 12. In every model that you're going to see from me, not only in this class, but in all the things I teach, all the predictors get centered. This may not have been something you've had to do before. But you always want to have an intercept that means something. And in models where the intercept turns into a variable, like in longitudinal models, multi-level models, not centering can cause that thing to go crazy and not even converge. So centering gets to be more important the more complicated your model is. So this person, now we have a better prediction for them. We predict that they should be 28.4, which is closer to where they are than 17, but still we have a ways to go. So their residual is now, relative to this line right here, 30. Another way of saying it is that part of their offness from the mean has been explained by their education level, but there's a whole lot remaining. The model says they should have made $30,000. They didn't. So why is it? What else do we need to know about them to be able to predict their income? I don't know, a bunch of other stuff. So if we do this for everybody, then we can compute the variability of the e's from the blue line, so the difference from each observation to where the blue line says it would be, and that, if the predictor is useful, should be less variability. And in this data set, we go from 190 to 162. I can compute the proportion of variability that has been explained by saying what it was minus what it is now over what it was. This is known as adjusted R-square. There's a different way to compute it for regular R-square, but this one generalizes to other types of models. And 0.17 is the answer. So another way of saying this is that education is responsible for 17% of all the reasons why some people make more money. That leaves, if I'm doing my math correctly, 83% for something else. Okay, how are we doing so far? Okay. So then making the model more complicated in general linear models means adding more predictors. So we have y sub I is a function of an intercept, which if you have more than one x, how do I interpret that? And feel free to read from the screen, because the answer is up there too. What's beta 0 if I have all of these x's here?
Beta 0.
Go for it.
The intercept?
The intercept, right, but like what's the definition? It's always the intercept.
When every other variable, all the x's are 0.
Yeah, all the x's are 0. So it moves around depending on what else is in the model. Another way of saying that is that it's conditional. It's the idea of a conditional mean, meaning for this kind of person, this is my predicted outcome. The job of the rest of the model is to say, but what about that kind of person? Oh, well then I need to condition it and move it up or down as a function of the person's other predictive information. E is always what's left. So E is always the difference between what the model says your outcome should be and what it actually is. Another way of saying what the model says it should be is y hat. So this is an abbreviation technique that simplifies formulas. We know that all this stuff goes into y hat, and then E is the difference between y and y hat. So a slope then, we talked about this last time. Difference in y for a 1-unit change in that particular predictor. And I have a note up here that sometimes when you see the abbreviation GLM, it stands for generalized linear models as opposed to general. And yes, that's confusing, and I'm sorry. I didn't make up the words, though. Usually you can tell that it's what it is based on the context. But when I say GLM, I mean general. I always put the I's out as a separate unit. General is nested within generalized. So when you're talking about when you're describing a model, like you're writing a results section or making a presentation, each fixed slope has multiple pieces of information that you would want your reader to have and that it's your job to interpret. So there's two that are essential. For every fixed slope, you want the estimate, meaning what is the best guess as to what the slope should be given our data. In the world of regression, the best guess is the one that makes the e's collectively the smallest. Another way of saying that is that it minimizes the sum of the squared e's. That is equivalent to saying it makes the data the tallest in maximum likelihood estimation. Same idea. Beyond that, though, we need some indication as to how precise of an answer that is. Is it like the slope is 2? Or is it like the slope is 2? 2-ish? That comes from the standard error. So that describes the expected inconsistency. How far off is the slope on average in any one sample from what it's supposed to be in the population? Where smaller means that it would vary less from sample to sample, and we have a better chance at saying exactly what it should be in any one sample. So smaller standard errors is better. These are the two pieces of information that you have to have, because everything else on this list needs those two things as an ingredient. Next thing over, if you're looking at a table of results, for instance, in your program output, is the test statistic. Usually it's called a T. Sometimes it's called a Z. But it's the estimate divided by the null hypothesis, which is usually 0, divided by standard error. So this thing is giving you an indication as to how many standard errors your estimate is away from the null. Where 2-ish is usually a dividing line for where we say, yeah, that means it's really unlikely to have come from the null. Sample size and number of predictors is denominator degrees of freedom. So n minus k, that's the number of possible slopes that you could have in this data set. Like if I have 100 people and I estimate a model with 3 slopes, then I have 100 minus the 3 slopes minus my intercept, because I always have the intercept. That means that I could add 96 more slopes, potentially, and then I would have explained all of the variance in my data. So denominator degrees of freedom, you can think of it as like points or like money. It's like how much is left over to spend. If I have all of that, then I can look up a p-value. For better or worse, p-values tell us how likely our result is if the null hypothesis is true. So if there really is no slope in the population, if it's really 0, how often would we have found the one that we had? Where traditionally less than 5% is the judgment line where we say, yes, sufficiently unlikely, I'm calling that thing significant. Question from the Zoomers, what's the difference between a T and a Z? So when would my estimate divided by standard error be treated as a Z instead of a T? When I'm not using denominator degrees of freedom. That's the difference. It's literally the same number because it's estimate over standard error. It's the distribution you compare that to figure out where 5% is. T takes into account how many people and how many slopes you've spent. Z doesn't care. In generalized linear models, most of the time you will see this as a Z instead of a T. So part of this process is trying to prepare you for that switch. It's a consequence of those models basically assuming that you have a lot of people or you wouldn't be trying to do this in the first place. Denominator degrees of freedom are available in some software packages for these models, but not all. Okay, how are we doing? Sounding familiar? Familiar is good? Please tell me if there's anything that's not familiar. Thumbs up, thumbs zoomers, excellent. Confidence interval. Well, the ingredients to a confidence interval is what reference T you're using and the standard error. So you can make a confidence interval for any level of confidence. I personally hate these things. I don't find them useful. But if you need to put them, Most software will spit these out for you, and here's the formula for that. So the idea that we take our t value and we compare it to a reference critical value, another way of phrasing that is with a univariate wall test. So that's the primary way that we judge significance in per slope, is to look at the p-value that comes from this t estimate over standard error. All right, standard errors, where do they come from? Standard errors come from variance left over in general models. So the residual variance of y is the numerator, divided by the variance of the predictor that the slope is 4. So it's trying to put it back into the scale of the predictor variable, because you have to know what a unit is to interpret how big of a standard error you should have. Are you talking about years, dollars, pounds, number correct? Like, what's the unit? Variance of x steps in to address that issue. Then sample size. So n minus k, where n is the number of people, k is the number of fixed effects, counting the intercept as well. So all things being equal, more people, smaller standard error. Less variance left over, smaller standard error. Once you have more than one predictor, the standard error picks up an additional piece of information in the denominator. It's not just enough to know what the scale of x is. Now we have to know how much of x is redundant with the other predictors. You've heard about the idea of collinearity, the boogeyman. Collinearity just means your predictors are related. The more related your predictors are, the harder it is to figure out what they each bring to the table independently. There's nothing you can do about that. Like the collinearity boogeyman, like I don't subscribe to that viewpoint. If your predictors are perfectly correlated, okay, you can't keep them all. If your predictors are very strongly correlated, you might only be able to keep one in one model and substitute it for a different one in another and talk about like which model might be preferred for whatever reason. But just keep in mind that this idea here, unique variance of x, comes into play. So all things being equal, a predictor that is less related to the other predictors will have a smaller standard error and be more likely to have its slope be significant. So yeah, best case scenario, x is uncorrelated with the other predictors. All right. Effect size. Did you talk about effect size in your previous coursework? So effect size is going to be different in generalized models because this idea of variance explained is only possible when you have an estimated variance in the first place, like in general models here. But it's not enough to just say, my slope is significant, p less than 0.05. That if you read some people's journal articles, like that's what it says, and that's basically no information at all. Marginally better is, I have a positive slope, p less than 0.05. Okay, well at least I know if x goes up, then y goes up, that's more information. By how much? How much does y go up if x goes up? Well, in order to answer that question, you have to know what the units are. So it's like, is it, how many thousands of dollars per year or what? If you want to be able to talk about how useful a given predictor is, there has to be a way to put it onto the same scale where you're correcting for differences in units. So effect size is designed to do that. It's a way to convey what is the strength of the relationship in like a unit agnostic way, like a standardized way. So effect sizes are essential pieces of information that go along with the estimate, the standard error, p-value if you want, and then an effect size. It helps you compare across predictors and compare across studies if you're trying to do a meta-analysis. It also helps you anticipate power. What's power? Do you remember this? Statistical power. Opposite of a type 2 error. What's power in a nutshell? Go for it. Feeling brave?
I guess it's how useful or the explanatory power of your study is based on the number of the sample size.
Based on sample size and effect size as well. They both make power go up. All of that is true, but that's not a definition. I don't disagree with you, though. Go for it. If you have enough people to find an effect, yeah, that's closer. It's the probability of finding an effect of a specific magnitude if it's really there. Missing an effect that's really there is a type 2 error. So it's the chances in which you can actually find what you're looking for. And you are more likely to find what you're looking for if you got more people, or what you're looking for has a stronger signal. So you can end up with slopes that have a relatively large effect size that are nevertheless non-significant because you don't have enough people. The slope isn't precise enough. The standard error around it, it's just too wiggly across samples. But if you have an effect size, then you can try to anticipate how many more people do I need to have a decent shot at finding this. So effect sizes help in future planning as well as just describing what you actually did find. In general linear models, there tends to be two families of effect sizes used. There's a D family, like Cohen's D, for instance, Hedges G. Anyone think of the others? There's like everybody had their own variant of it. Like we took the D and I'm going to tweak it and call it my letter. And I'm going to tweak my letter and call it your letter, like that whole thing. D means standardized mean difference. So it's useful in two group situations to talk about how many standard deviations different two groups happen to be. A more general effect size metric is the R family, otherwise known as eta. Those are synonyms for all intents and purposes. Like eta squared, partial eta, semi-partial eta, all that stuff. That's in a correlation metric. So what is the strongest correlation that you can have? I'll accept two different answers, by the way. 1 is one answer. What's the strongest? -1, yeah. What's the weakest that you can have? 0. Yeah, so if I tell you that I have an effect size of 0.8, like, you know that's big. I don't have to explain any more than that because it's a metric that everybody understands. Something that you may see in general linear models but are going to be effectively discontinued are standardized slopes. Those are a problem. I have a whole thing about that in my other class, and I can go into it if you care, or else I posted a link to a blog post that explains it better than I do. But standardized slopes are not really standardized because they're not really bounded in a correlation metric. Those are not going to be a thing in moving into generalized models. Those stop being a thing. The good news is that you can use the output that you have to get effect sizes directly. So you can take your t-test statistic for any slope that you get from estimate divided by standard error and turn that thing into a D, turn that thing into an R, and you can turn Ds and Rs into each other. So why that's useful is because a lot of times you're interested in quantities that aren't directly part of your model, they're indirectly part of your model. As an example, and we'll do an extended example with this, but just to get you the idea, let's say that I have 3 groups, and I'm interested in comparing an outcome across 3 groups. How many slopes do I need to put in my model to make that work? How do I represent differences across 3 groups as a set of predictors? How many slopes do I need? Oh, fewer than that? If I only have 3 groups? 2. Because I've got an intercept is going to be the mean for one of them, a slope to get me to the second group, and a slope to get me to the third. So depending on how I code the model, I might get the difference between group 1 and 2 and 1 and 3. But then the model doesn't directly tell me 2 versus 3. I can get that. I'll show you how. It's one of the things I did not learn until way too late, and so I put it in the very beginning because it's super useful. You don't have to rearrange the model to get the extra pieces of implied info. It's in there. So that means if you know how to ask for a significance test for the missing pieces, you can get an effect size for those 2. By the way, if you've heard the terms partial versus semi-partial, those differ with respect to a denominator. So if you take your R and square it, then that becomes something called eta squared. R squared is the same thing. And if that is relative to all of the variance that used to be in your outcome, that's called semi-partial. That's more fair. If it's relative to only the E unexplained variance, that's called partial, and that's less fair. Because then it depends on how good the rest of your model is, how much E is left over. So we're not going to have eta square kinds of things in generalized models because we don't have an estimated variance in most of these cases. Having a separately estimated variance for how much information is left over, that's assumed to be constant across all the observations. That's only a normal distribution thing. Once you step away from that, variance is not often an estimated quantity because it's not constant. So that means any R-square looking kinds of things aren't possible in an unambiguous way. Okay, all right, how are we doing? Still sounding relatively familiar? Thumbs? Thumbs up? Okay, Zoomers, any questions from you guys, folks? No? I'm watching the chat, I promise. All right, scaling. How we put predictors into a model. Rarely is it the case that you can put a predictor variable directly in a model the way it was stored in your data set. Like almost never. This is something that you'll have to think about ahead of time to make sure that your choice makes sense in terms of how to represent the information and makes sense in terms of what you want to know about the predictor. So in my world, we always rescale predictors so that 0 means something. If you have a variable in which 0 is already meaningful, you're good to go. Right? Like if it's number of classes we're going to be on Zoom this semester as my variable and the answer is 0, that means something. Number of pets in my household, the answer is 0, that means something. But if I'm talking about like my attitude about something on a scale of 1 to 5, I can't have a 0. So I have to move the scale of the variable so that 0 is somewhere in there. So this is necessary always to ensure that we have an intercept that means something. Because the intercept is the expected outcome when the predictors are 0, always. It's also going to matter in models with interaction terms, which is one of the topics that I want to hit pretty hard in this review unit, probably next week, based on my timing thus far. And just as a side note, it's also necessary in conducting multi-level models, which are models where you basically have like regression lasagna, like layers of regressions happening at the same time, where you have more than one dimension of sampling. So if you have something like students nested in schools, then you have an E basically at the student level for why students differ from each other that you can predict with student information. But you also have the analog of an E across schools. Like why do some schools have better outcomes on average? You can predict that with school information and see how much of that is left over. In those models where you have multiple types of residuals, not centering can cause estimation problems. So for quantitative predictors, centering. Subtracting or adding a constant so that 0 means something. That is what centering means in our class. There is more than one kind of centering, which is why I have the parenthetical here, constant centering. The key idea is that you are subtracting or adding the same number for everybody. So you can pick the sample mean. That has its own name. It's called grand mean centering. That's fine. You can pick the minimum value. So if I have something like a 1 to 5 point Likert scale, then I might have 1 as my centering point, because then I can talk about what's my expected outcome for someone who has the lowest answer, and then talk about what happens as the answers move up. You could pick any meaningful value, like education. 12 years of education in the US means a high school diploma. Like people know what that means. I might have a mean years of education of something like 14.67. Now I could make that my reference point, and my intercept would be the expected outcome for someone who finished 14.67 years of education. It's not wrong, but it's weird, because nobody wrote that down. So picking some constant within the scale of the variable that means something is what we're going to do. For categorical predictors, though, this is different. This is what's known as coding predictor variables, where we have to cut up the predictor into binary 0-1 sub-predictors to represent differences between categories. So if I have capital C categories, then I need C-1 slopes to be able to fully differentiate each category's outcome. Why is it -1? Because I got the intercept already. If I have the intercept, then I know what the expected outcome is for at least some people, and I only need C-1 slopes to get it for everybody else. So you can do what's known as dummy coding, where all of the values are zeros or ones, or you can do things that are known as effect coding, where it's a combination of zeros, ones, and minus ones. Did you do this stuff in your previous coursework? A little bit? You did. You're
Yeah.
definitely nodding. Anyone
Yeah.
else? A little bit? Maybe? This is a very common thing. Sometimes people teach it to let the program figure all of this out, and sometimes people teach it to make you do it manually. I am solidly in the manual camp. Once you get really good at it and it's tedious, then you can let the program do it. That's my philosophy. I don't like effect coding. I'll just tell you that right now. I don't do that. I only do 0-1 types of coding. I don't like the idea of having the intercept be the average across groups, because nobody is in the average of the groups. Everybody's in either one group or another. So it's weird to me. If I have C-1 slopes, this will perfectly recreate all means for the outcome for each category and all mean differences. Any that are not directly given can be found as linear combinations. So here's one example of a dummy coding scheme that you've probably seen. This is from the regression, the textbook that I use in my intermediate regression class. It's on your syllabus as a recommendation, and one of the chapters from it is on your reading list for this week. What's known as indicator coding in their language. This is the idea of denoting one group as your reference, and then having each variable tell you how different another group is from that reference group. So if I have groups A, B, and C, and I want to know if they differ on my outcome, then the three fixed effects that would allow me to do that is I need an intercept, beta 0. In the linear model equation, beta 0 doesn't multiply anything. It just goes straight in. That means it applies to everybody. Another way of thinking about it is that beta 0 multiplies a column that would just have a 1 for everybody. And if you represent these models using matrices, you have to have that one column in there to work. Let's say that I want group A to be my reference, who the intercept is going to become for. That means that I make two new variables in which group A is zeroed out, as indicated by the green here. Then one of my variables, I named it A versus B because that's what I want it to mean. I give a 1 to the B group and I give a 0 to the C group. Now if I just had this much right here, is this going to give me A versus B based on this pattern of zeros and ones? If I just had this column, what do you think?
No, because you have to have A.
Yeah, right now this is A and C together versus B, if I just have this one. So I need another one that pulls apart A and C. So this last column I'm calling A versus C because when it's combined with the other one, that's what it's going to mean. So this is probably the most common way to set up categorical predictors in a linear model, is to denote one of them the reference, and then each of these slopes says how different the alternative group is from the reference. I will say this deliberately multiple times. The slope tells you how the one group differs from the 0 group. And you have to say it that way, otherwise the direction is backwards. Yes, sir?
But in averages of B, A versus B, that wouldn't exactly tell you like what the value of C is for that column, right? Or what it is.
Say that again?
So in A versus B,
Mm-hmm.
since A and C are joined together,
Mm-hmm.
that wouldn't tell you like what the average for C would be. Is that
No,
correct?
if all I had was this column, then I have screwed it up. Because this column differentiates A and C together against B. And that's not what I want. So that's why I need to pull the other column in here to pull those two zeros apart. And you can think of it this way. If all I had was A versus C, that's not what this would mean. It would be A and B combined versus C. And then I need this column to pull A and B apart. So it honestly doesn't matter which way you set it up. Eventually you can get to the mean for each group, because the mean for B is A plus this slope, the mean for C is this one plus this one, and the difference between B and C is going to be this column versus that column. That one is a linear combination that you have to ask for, but it's still implied by the model. So this type of coding scheme is useful for nominal variables where there's no ordering. Like A, B, and C are not in any sort of order, they're just different kinds. If you have a variable that is ordinal instead, then this becomes less useful. If it's ordinal, if it's ordered, you might want to know the differences between subsequent categories as you move up the order, such as for a 5-point Likert scale. So let's say that I have a variable, how happy are you, from a scale of 1 to 5, where 1 is like not happy, 2 is a little happy, 3 is yeah, 4 is happy, and 5 is I'm awesome. Like, those aren't numbers, right? Like, even though I put a 1, 2, 3, 4, and 5, they're not numbers. They're kinds, but they're ordered kinds. So if I have something like that, I might try a different coding scheme known as sequential coding, where here I have decided that the I'm not happy number 1 group is my reference for the intercept, and I have to have 4 slopes to fully differentiate my 5 categories. If I do this, then I can set up this slope to represent the difference between a score of 1 and 2. So that's the point at which the 0 switches to the 1. The next variable over tracks the difference between 2 and 3, because that's the point it switches to a 1, 3 versus 4, and 4 versus 5. So in this scheme, not everything is being compared back to 1. It's being compared to the next one. So you can then test, for instance, can I just call this a number and be done? Well, another way of answering that question is the difference between 1 and 2 on my outcome the same size as the difference between 2 and 3 as between 3 and 4 and 4 and 5? If all of those differences are the same size, then yeah, draw yourself a line through the whole thing and call it good. So another way of thinking about, can I treat this as interval rather than ordinal, is, are the sizes of the successive differences the same? Because if so, then a single line will work. If not, then you need like piece lines that all have their own little slopes. So this coding scheme works because after a variable has switched, it stays at 1. Whereas like this one goes back to 0. And that's why these coding schemes give you different results. So I tend to do things one of these 2 ways when it comes to categorical variables, based on it being ordinal or nominal. Either way, because you have 5 fixed effects here for 5 means, and this one has 3 fixed effects for 3 means, you get all possible means, and the model can give you all possible mean differences, not just the ones that you coded. Okay, how are we doing? A little bit. An example might help, right? Am I right? Examples usually help with like numbers and stuff. Yeah, we'll have an example of this kind here in a little bit. Here is a table that is in chapter 10 of the Darlington and Hayes book that has other coding schemes. I have never tried to use these or understand them, but I put them out there as other choices for you. And one of the articles on your reading list has even more ideas as to how you can code categorical predictors to talk about that. So it's totally up to you how you set up the model. The question is, what do you want to know? Which group differences are the most of interest and which ones are sort of secondary? Code the variables so that you get the ones that are the most of interest. All right, so here's what it would look like then, sort of generically, and then we can look at an example. Let's say that I have this type of linear model here, where I have a 4-category grouping variable. I have a control group and then 3 flavors of treatment. Not sure which one's going to work best. Let's try them all out. So these are, each person is only assigned to one group or the other. First off, if I wrote this equation right here, what would be another name for it? If each of these D variables is a dummy code differentiating groups. What might someone call this model by another name? I have a 4-category predictor variable and a continuous outcome. Starts with an A.
ANOVA?
This is an ANOVA. This is a linear model representation of an ANOVA. More specifically, a one-way ANOVA, because I've only got one grouping variable in the story. So let's say that I'm interested in control as my reference, and I want to directly see how effective each treatment is relative to control. That's the most important thing to me, so I'm going to set up my variables this way. So the 0 group would be for control. D1 covers the difference to get to treatment 1. D2 is the difference to get to treatment 2. D3 for treatment 3. Cool. So then how does this model provide us with what the mean's supposed to be for each group? Like this. Beta 0 is always the expected outcome when your predictors are 0. In this context, that is for the control group because they have a 0 on all 3. So beta 0 is going to give me directly what the mean is for the control group. To get to the treatment 1, 2, or 3 means, those are linear combinations. They each start with beta 0 because beta 0 goes to everyone's score regardless of what group you're in. Then the slopes kick in. If D1 is 1, meaning if we're talking about someone in the first treatment group, beta 1 says how different that group's score is going to be relative to control. So what if this is an outcome where treatment should make the scores go up? Is beta 1 going to be positive or negative? If scores are supposed to go up if you've been treated, should beta 1 be positive or negative in sign? Positive. What if this is something like delinquent behavior and we want the scores to go down after you've been treated? Then beta 1 should be negative. So that's why I keep phrasing it as how the 1 group differs from the 0 because the sign tells you who's higher. The p-value will be the same either way, but you got to know who's higher to interpret what your model's telling you. So beta 1 kicks in, so to speak, if D1 is 1 and not otherwise. Beta 2 kicks in if D2 is on, and beta 3 kicks in. So each of these treatment means is a linear combination of the intercept and the slope to get to its difference. If I have 4 groups, how many possible differences between pairs of groups do I have? Well, I got 3 right here. Control versus each of the treatments, there's 3. Are there more possible pairwise differences I might care about?
Yeah.
How many more? Yeah, finger counting is allowed at this point, right? There is a formula for it, but I don't have it memorized off the top of my head. It's like n choose 2, basically. It is, how about 1 versus 2 and 3? That's 2 more. Let's see, yeah, there we go. Control versus each of these is the first 3. Then group 1 versus 2, group 1 versus 3, and last but not least, yeah, 3 versus 2. So I got 6. Now, how many of those 6 do I get directly on my output as model parameters that I set up deliberately? 3. Now, what about the other 3? How do I get those? Did you learn how to do this before? Not an interaction yet, because this is just one variable, but that's coming. See, I never learned how to do this. When I was learning how to do these things, I either fitted into an ANOVA package where it just spit out all the means and mean differences and I didn't have to know how they got there. Unfortunately, that choice is not always available in generalized modeling software. So you do need to know how to do this sometimes. The other way that I learned how to do it is to try to hack this problem. Well, if I want to know about all the differences relative to treatment group 1, what if I change my coding scheme so that they're the 0? Could I do that? Sure, I could. Any one of my 4 groups could be the reference, doesn't matter. If I set it up so that the first group here, treatment 1, the first treatment group is my reference, then all of the slopes would tell me how it differs from each of the others. And then I could repeat that process for treatment 2. And across 3 models, I would get all the pieces that I want. Well, that sucks. No, you can get it out of one analysis. So here's how it works. If the model tells us how each group gets its own mean, it has to tell us how each group's means differ at the same time, because I've got all the pieces of information I need. So if I want to know control versus treatment 1, for instance, or 2 or 3, these are the easy ones. Because I know what the mean is for the reference group, that's beta 0. I know how the alternative groups means differ, that's beta 1, 2, or 3. Beta 0 plus beta 1 minus beta 0 just leaves this one. The others, though, can be found the exact same way. So if I want to know treatment 1 versus 2, then I get the mean for 2 minus the mean for 1, and it's this beta 2 slope minus the beta 1 slope. That's my answer. 1 versus 3 is the beta 3 slope minus beta 1 slope, and so on. So you can take the two slopes that refer to the groups that you're interested in and find their difference, and that is the missing group difference. Now, I can do the math. Like, if you give me a table of means and a calculator, like, I can figure this out. But what's harder to figure out by hand is what the standard error would be for those model implied differences and the p-value that goes with it. Turns out, this is a line of code. You ask for this. Every statistical package on the planet has a way to do this. You just have to know how, even SPSS. You can ask for what is known as linear combinations of the fixed effects. And this is one instance in which you would do so, is to get the model implied, not directly given, group differences. I'll show you how to do that in Stata and R, and I have how to do that in SAS as part of the online download packet for the example that goes with this. So there's two ways that you can put a categorical predictor in the model, and this is one of them. This is what I'm going to favor. If you know how to do it a different way and you're comfortable with that, Godspeed. But for folks that are just getting started, this is the way that I prefer, is to manually create these additional predictor variables that differentiate the groups. That way you have complete control over what they mean. You can set it up into whatever pattern you want. And those predictor variables then are treated by the program as quantitative. The program doesn't know that they're dummy codes. It just knows that it's a 0 and a 1. The reason that's okay is because there's only one difference between 0 and 1, so you're not making any weird assumptions. The other reason that I like to do it this way is for transparency. This method of deliberately creating your dummy-coded predictors directly corresponds to the linear model representation in a way that letting the program do it does not. The alternative, though, is to let the program do the dummy coding for you. So that is what is happening under the hood in, let's say, SPSS syntax, the by command or the fixed factors box. If you put a variable on the class statement in SAS, in Stata, if you use I dot as a prefix for your predictor, or if in R, if you denote it as a factor variable. It is making the dummy codes for you. What the reference category is varies by program. In SAS and SPSS, it's the highest or the last of your grouping variable, either alphabetically or numerically. In Stata and R, it's the first. You can change it, but it's good to know what the default is because that colors what you're going to get back. This can be more convenient if you have a lot of groups. So once you get the hang of this dummy coding and you have like 10 groups, you're like, do I have to really make 10 variables and do this whole thing? No, you can let the program do it. But then there's some potential weirdness with respect to what your results mean in the face of interaction terms. And that, I want you to be prepared for that weirdness. The question is, if you have an interaction term with group, does the main effective group refer to the average group difference or the group difference specifically between one of the zeros and the ones? In certain parts of the output, it's one, and in other parts of the output, it's the other. So you can end up with two different p-values for what's supposed to be the same thing. So when you tell the program that you want it to do the dummy coding, this is what it's doing under the hood. It is making a new dummy coded variable for every single group. These dummy coded variables are not in your data set unless you somehow ask for them to be saved. But this would be the meaning of each of these variables in the rows here. Is control would be look like this, is treatment looks like this, and so forth. So that means then one of these columns is redundant with the intercept. Which one gets dropped then controls who your reference is. So if you drop treatment 3, then they're the reference. If you drop control, they're the reference. If you drop the fixed intercept, you can keep all 4. And yes, there are certain situations in which that's a preferable way to do it, is to drop beta 0 out of your model and just have these. Then what your model gives you are the means directly and not the mean differences. Last but not least, what about amounts and kinds at the same time? Semi-continuous predictors. So what if you have something like number of cigarettes smoked each day, same example I beat to death last week, and you want to differentiate whether or not someone is a smoker and whether or not they are a heavy smoker? Well, I can make 2 new variables that do that. So let's say that this is my count of cigarettes here in this column. I can do one variable that's, did you smoke at all? No means 0. Something means 1. Then, if you're a smoker, how many cigarettes did you smoke? That one's different. This differentiates somebody who smoked 1 cigarette from more than 1. And then both of these variables go into the model at the same time. So the first column would tell you the outcome difference between smokers and non-smokers, smokers who only smoked 1. The second column then tells you what is the effect of being a heavy smoker. For each additional cigarette, what happens? So this is known as piecewise slopes or linear splines. This is much more common in longitudinal studies where they're looking at carving up time into sections, but it can be useful for other situations. And I will guarantee you're going to have at least one homework assignment where you have to do this. That's why I'm showing it to you today. Here's what the code would look like to generate those columns in all 3 packages that I'm familiar with. So if I'm in any of my packages here, I wrote the code the same way. The first thing would be to define the new columns and set them equal to missing values. Then replace those missing values conditionally based on the number of cigarettes column. So if the number of cigarettes is 0, then my smoker column is 0 and my smoke amount column is 0. That would do this first row here. So the first 2 conditions in this here, and the first line in SAS, and these 2 right here in Stata. And then the next one, if they smoke greater than 0, so they smoked at all, then it's cigarettes minus 1 to create this column, or smoker equals 1 for this one. So there's a lot of situations in which going from nothing to something matters, and then how much of something is the research question. You don't have to divide people into arbitrary groups. You can have both groups and kinds at the same time with this sort of coding scheme. Cool, huh? All right, 310, we're hanging in there. Everyone still awake? Maybe? A little bit? Yeah, sideways? Yeah, the 310 sideways. It could be worse. This class could start at 4:30. I know, that was the worst class I had in grad school, was 4:30 to 7. I was like, I love this stuff, but like at 6 at night, like I'm just done. I can't even talk by then, let alone sit and listen. So 3:10 is a good time to stop. So questions before we call it a day. We'll continue with our review next time and look at some examples of how to do this with data. No questions so far, or anything that you want me to say again? The reason my slides are so packed, by the way, is that I'm hoping you can sit and listen and think as opposed to like scribble furiously. So the fact that you're not writing is actually a good thing in my book. Question?
Yeah, so when you were talking about like the manual indicator coding,
Mm-hmm.
like on slide 12, if you did the
Slide 12? Mm-hmm.
sequential coding, would that also give you those results? But it would just be like more intensive on the initial like coding and setup side? Or like are those 2 different things that we're doing?
So the question was, if I did sequential coding instead, could I still get all the differences?
Yeah, like is it the same thing basically? Like are these just 2 different ways of accomplishing the same thing, which is like figuring out like T1 versus T2, T1 versus T3?
Yes. Either, go back to that slide. As long as you have C-1 slopes, you will get all C category means back once you have the intercept in. And then it's the question of which ones do you want the model to tell you directly and which ones do you want to have to ask for after the fact. So the same logic would apply to figuring out how to get the model implied differences. Say for here would be like, for somebody of a 1 versus a 4, right? You're not going to get that directly, but if you work through the logic of how the mean gets predicted for each of these, you could get it indirectly as a difference. So the exact equations would be different based on what your coding scheme is, but the logic is the same. If your model tells you what the mean is for each group, it has to be able to simultaneously tell you what the mean difference would be, because that information is baked into there. It's just a question of what you're getting directly and what you have to ask for. So that's why knowing these choices, usually people are interested in some more than others, and it's a lot more convenient if those are the ones that pop out on your output, especially if you want to look at moderation of those effects by other variables. Having that to be built into the model directly is a useful thing. Okay, does that help? Okay. Anything else before we call it a day, but not a week, because it's garbage day? That means I say, see you Thursday, as opposed to have a good weekend. All right, then, happy garbage day. Thanks for being here, folks. I will hope to see you Thursday. Let me know if I can help you with anything. Bye, Zoomers.
I'm going to.
What else do we have? Multiple slopes. Ah, good. Two more. Almost done. All right, Vladimir, let me please